Sir, shall we start in a minute? Sir, shall we start in a minute?
వెంకటరెడ్డి సార్ రావనా
ఓకే సార్ ఉన్నారు అనుకుంటాను సార్ వెంకటరెడ్డి సార్ మ్యూట్ ఎస్
చూస్తున్నా.
ఉన్నారు ఈ అన్మ్యూట్ సార్
Yes, good morning to
గుడ్
everybody.
మార్నింగ్
I
గుడ్
am very
మార్నింగ్
much here.
యువర్ సార్
Yes, sir.
గుడ్ మార్నింగ్ సార్ we are going to shall we start the session sir
Yes, yes, yes.
yes okay sure. Welcome back everyone. We are here for the second session of the day 1. Introduction to Quantum Computing with background of Quantum Mechanics by Dr. P. Venkatreddy. Let me take the privilege of introducing him to all of you. Dr. P. Venkatreddy, working as a professor of physics and head science and humanities at Srinidhi Institute of Science and Technology. He has vast experience of 36 years in teaching and has published many papers in national and international journals. Under his guidance, 2 scholars have been awarded PhDs. Sir, we are privileged to have you here in this FDP. Will you please start, sir?
Can I?
Yes, sir. Yes, sir. Yes, sir.
Respected principal, director, IQAC, respected HOD of mathematics and their team, untiring efforts made by the team of mathematics section and all distinguished participants. I'm really happy. I'm excited to hear from the words, the technical words from mathematics teachers. I think that there is no difference between mathematics and physics. I can say the mathematical sciences. I used to tell the students and my colleagues that without mathematics, probably we would not have seen all these developments so far, that what we have seen and what we are witnessing now. And I myself feel very proud that I was a fraternity, teaching fraternity of CBIT, and worked for about 14 years. And 3 years, I went to Usman University to pursue my PhD. Later, I came back to CBIT and served for 6 more months and left to Srinidhi. And I am there right from its inception in Srinidhi. The question is here, introduction to quantum mechanics. It's a wonderful topic. So before I speak about the quantum mechanics, I can say before 1900 and after 1900. And before 1900, many theories were there, and all theories were treated as classical theories and classical models. And with these classical models, we were able to see many applications, and mankind was surviving with the various applications of classical theories. Classical theory includes basic mechanics, optics, electromagnetism, electromagnetic induction, electrodynamics, and so on. These theories were able to explain successfully the number of concepts by which we were able to we were able to construct and implement the various equipment for the betterment of mankind. Mechanics, I think without mechanics, we cannot move a single step for the taking of examples of like designing of pumps, compressors, like automobiles, or like aerodynamics, aircraft engines, and so on. This is, of course, mechanics related. Then coming to the like optics, that is electromagnetic radiation, where you can study the basic laws like from school level to college level: reflection, refraction, total reflection, dispersion, like mirrors, lenses, optical instruments, and so on. And various applications of this particular optics still we are experiencing even today. If you take mirror like a two-wheelers or four-wheelers, if you see the convex mirror is fixed as a side mirror. Then coming to the defect of vision can be rectified by the lenses. The defects may be of various types, maybe short sight or long sight, or maybe both. Short-sighted person can see the closer objects but not longer distant objects. But longer distant objects are rectified with the suitable concave lens. Whereas long-sighted person can see the longer distant objects but not shorter distance objects, still can be rectified with by using suitable convex lens. And there are possibilities that the persons may suffer with both the defects, and such defect can be rectified by bifocal glasses. The upper part will be rectified with one lens and lower part will be rectified with the other kind of lens. This is one part of development. Then microscopes. The microscopes are constructed to see the minute objects like bacteria or blood cells or pollen grains and so on in a magnified way. Whereas the longer distant objects can be also seen by telescopes. That's what astronomical telescopes or terrestrial telescopes. This comes under astronomy. And we can study the properties of planets by using telescopes. This is the area of optics. Then acoustics and sound. Types of vibrations, resonance, speed of sound, an elastic medium, and so on. These all basically were developed during the year, during the period I can say 1643 to 1727. The great scientist, Sir Isaac Newton, and he inspired entire world undoubtedly, and everyone experiencing the various applications in their day-to-day life, even today, that is after 350 years. And you can see the a photo of Sir Isaac Newton. See, he discovered the basic laws of motion. That's what we can call Newton's laws of motion, laws of optics, and invents calculus. You know very well that how much importance is there for calculus even today. That's what basically he was a mathematician and a multitask person. And in those days, I think he did lot of work and in the domain of mathematics and in the domain of various physics applications. He used to work for mathematics and apply that mathematics concept to the physics applications. So these are all applications, whether it's the mechanics or optics or sound and so on. These all, I think, will be, I can say that these all will be existing forever as long as universe exists. So I think the great Newton has inspired, as I said, the entire world. So as a teaching fraternity, all we must be happy that we are part of the knowledgeable members in the society and imparting education to the student community. So I think the applications part, we have to focus and later. This is one part I said, this is before 1900. And these all things you can explain successfully in a bulk way. That is for bulk matter. Bulk matter, or in general, we can call it as technically macroscopic. So macroscopic objects, I think, were taken and explained successfully till 1900. And after 1900, then after 1900, what happened exactly? So let me explain little for a few minutes. The 1901, the quantum theory came into existence and it was proposed by Max Planck. And Max Planck could succeed in explaining the quantum theory because it was a new theory, was not accepted by the contemporary scientists easily, and he was able to explain and connect the classical laws with his own new theory and satisfy the classical concepts which were developed earlier. Then people had accepted the Max Planck's theory in 1901. And of course, for his invention, he got a Nobel Prize. And but for I think until 4 to 5 years, the Planck's theory was not realized by not realized means that the importance of Planck's theory was not recognized by the people. The great Einstein in 1905, he started explaining the different concepts and he presented three papers in three different domains. One is general theory of relativity. The second one is stimulated emission of radiation. Third one is photoelectric effect. The greatest thing and interpretation of Albert Einstein is that matter, the radiation, especially radiation, cannot interact with wave, but radiation can interact with matter. Or in other words, particle only can interact with matter but not wave. But at in, by that time, the wave theory became predominant over the corpuscular theory. So, what was the corpuscular theory? Corpuscular theory was proposed by Sir Isaac Newton. That according to Newton, according to Newton, light or electromagnetic radiation consists of tiny particles called corpuscles. And this theory could explain most of the concepts of light, but failed at explaining interference and diffraction properties of light. And most of us know all these things. Most of us know all this in our college level. And the Newton, anyhow, as I said, that he explained the basic laws of light, and applications are extended subsequently later in number of ways. And but this corpuscular theory has failed in explaining the concept of interference and diffraction, and both were based on properties of wave. And wave theory could explain successfully the concept of interference and diffraction. Whereas Huygens proposed this wave theory and explained the basic concepts of light, including the interference and diffraction. That's how it became superior over corpuscular theory. Another important aspect of this theory is that the velocity of light decreases in denser medium rather than it increases. That I was mentioning about Sir Isaac Newton, that he proved the velocity of light that increases in denser medium mathematically. And he stated that in a denser medium, that light ray is going to be attracted strongly so that its speed can increase more and more in denser medium, it can increase. But it was found to be defective. The reason is that there were no experiments at that time, and the experiment name was Foucault's experiment, and Foucault, when explained about the determination of velocity of light, he has used the denser medium as water, and he found that velocity of light was decreased in water. So it is established that velocity of light always decreases in denser medium. That's how the corpuscular theory or particle theory was found to be defective compared to Huygens wave theory. So now I think we have to give a thought. Almost, I think, with certain gap, because now wave theory became dominant and cosmic theory became, I think, defective. But here, Einstein was dare enough to choose the particle character, and he had a strong idea that particle only can interact with matter but not wave. Then what particle has to be imagined? Then he took the Planck's law of radiation. According to Max Planck, the radiation consists of discrete and discontinuous bundles or packets of energies, and the minimum energy associated with radiation is h nu. That's what he derived from quantum theory. And but he has not given the name for the particle, because Einstein was in need of the particle character and a particle, and he named that particle as a photon. So photon name was given by the Albert Einstein, and he started explaining the electromagnetic radiation as streams of particles called photons, and and this particle nature is explained in his experiment. He did only one experiment, and that experiment is photoelectric effect, and he received the Nobel Prize for his small work. So he contributed a lot to the theory of relativity and the other aspects. And this, Einstein, while explaining the phenomenon of photoelectric effect, is there that I said, is said that wave cannot interact with matter, but particle only interacts with matter. Based on this, he took Planck's quantum theory as a base and interpreted that light consists of discrete and discontinuous streams of particles called photons. Here photo is given. I think where Max Planck is senior to, well, I think very much senior to the Einstein, to 25 years elder to Einstein, but both are theoretical physicists, basically mathematical background. They never worked on experiments, and also they stated that I think uh, theory, invention of theory is one part, and the realization of the theory will be accepted by the scientists or people around only when it is experimentally proved. Whereas if any invention is done through experiment, then probably I think they can go reversely for mathematical interpretations. But both the scientists are theoretical physicists, including even Newton also. But they have done the great job. And Einstein, what he mentioned is that was essential essence of discovery. The, a photon of sufficient energy, when incident on a metal surface, part of its energy is utilized to knock out the electron from metal to surface, and remaining energy is utilized to increase the kinetic energy of emitted electron. This he has interpreted in a mathematical form, that is like a photon is striking. Imagine a photon is striking the metal, and if a part of its energy will be utilized to knock out the electron from inner part of the metal to the surface, and it is called a minimum energy or work function. And the remaining energy, this remaining energy means that instant photon energy minus work function will be utilized to increase the kinetic energy of electron. This is what you can call photoelectric equation. H nu minus H nu naught is equal to half mv square. That's what photoelectric equation. And the various, I think, applications, number of applications today we are witnessing. It is basically the photoelectric effect application is like conversion of a light energy into electrical energy. So that's what solar cells, photovoltaic cells, photoconductive cells, solar panels, and so on. A lot of importance is there for this solar energy. Is what nowadays it is called non-conventional energy. So though it was discovered long back, maybe 120 years almost, but still, but it is a very important application in our day-to-day life today. So now coming to the hello, hello,
Sir. Audible, sir.
are you able to hear?
Yes, sir. Yes, sir.
Okay, okay,
Yes, sir.
okay,
It's clear, sir. It's clear, sir. There is some noises from the background. I think that is disturbing.
okay,
That's okay,
okay.
sir. We will take it. Yeah.
Yeah. So now the question is, I think I started my talk before 1900 and after 1900. Before 1900, about whatever the theories which were developed, applied for macro objects, I said, and now coming to the quantum objects. There's that, fundamental particles of matter. So that classical theory has failed to explain certain things. Here, very important point. I think whether it is like engineering graduate or mathematics or physics or chemistry, right? I think this very very important point. Classical mechanics, there's like for example like a force from Newton. If we apply, I think such mechanical force or even the force, large force is applied. I think that doesn't work for the microparticles. So quantum means here it is applicable for only micro nature or nano nature. Subsequently, it came to nano. Then micro nature means then we have to think of that is atomic level. That's what molecules are atoms, are isotopes, mesons, neutrons, and so on. And for these, because their size is too small and invisible, and they can be accelerated to the maximum velocity. But I, I think what kind of, first of all, the existence, because till 1927, nobody knows the existence of atom. Okay. And and there was no sufficient support or background to defend that the atom is existing. And this was first tackled by J.J. Thomson, followed by Rutherford, who most of you know. Then Niels Bohr. Niels Bohr started explaining of existence atom by taking, I think, three postulates. By taking quantum theory and a classical theory. Earlier two theories were based on classical, and this classical theory has failed there. So quantum theory became again prominent, not only at the time of explaining a photoelectric effect by Einstein, where he has named it as a photon, and the same photon concept is extended with a gap of another 25 years by Niels Bohr. And Niels Bohr, the of course, stated that as long as electron revolves around the nucleus, it neither radiates energy nor absorbs the energy, and that the atom absorbs or radiates energy. But when it jumps either from lower to higher or higher to lower, it may absorb or else radiates the energy. And the difference of energy is always given with the frequency, in terms of frequency, that is in terms of Max Planck's formula H nu, E2 minus E1 H nu. E2 is a higher energy and E1 is the lower energy. So that, of course, and later he has calculated the frequency of spectral line. Then he has explained successfully hydrogen atomic spectra, Lyman series, Balmer series, Paschen series, Franz series, and so on. Then subsequently, the spectroscopy has developed enormously, and many people were fallen in line for research. And this is what the importance of quantum theory, and this is what Max Planck's formula. So later, and coming to this, how this, I think, the radiation part and the matter, when it comes to matter, the de Broglie came later, and de Broglie just gave a bold statement that, that means hypothetically stated, that when electromagnetic radiation is exhibiting the dual character, why can't matter? This was the idea first was given by de Broglie. De Broglie, electromagnetic radiation means light only. Electromagnetic radiation basically has a broad spectrum from very high value of larger wavelengths to the very lower level of wavelengths, that in terms of like a visible spectrum, then beyond red it is infrared, Then beyond red, it goes like radio waves, TV waves, microwaves, and so on. This is what you can take. And on the other hand, below violet, ultraviolet, X-rays, gamma ray radiation, and so on. So this is what electromagnetic spectrum. So this electromagnetic spectrum now consists of streams of particles. Now, the streams of particles are photons, and that's when a photon moves with certain uh, when photon moves with the certain velocity, means the speed of light. It always associates with the energy, and that energy, according to Max Planck, is h nu. That's fine. And this h nu, how we can apply for the matter? Matter means here matter atoms and subatomic particles like electrons, protons, neutrons, and so on, as I mentioned. Then here again hurdle came. The importance of Planck's formula, I think, made to realize by Einstein. Then Einstein, by the time he derived the formula of mass energy relation, that's E is equal to mc square. I think everybody is familiar with the formula E is equal to mc square from theory of relativity. Now, by looking at the question, I think children nowadays, the school children can ask that a particle of mass m moving the velocity c, then what is the energy that is associated with the particle? Means that it could be half mc square, but it's not half mc square; it is mc square. So he derived mc square, and also he derived that various formulas for various things like time dilation, length contraction, and that relativistic mass. The relativistic mass is unknown. That's what m is equal to m naught by 1 minus v square by c square under root. This is the formula. And after deriving this formula, the Einstein stated that I think it is not possible to create anything from nothing. That, in other words, something cannot be created from nothing. And in case if it all is created something, it cannot be brought back to nothing. That is our greatness of Einstein. And not only he did, and he practically proved that, because a half mv square is there. Then half mv square is the standard formula. Today, kinetic energy means half mv square only. Now you look at this formula. That's m is equal to m naught by 1 minus v square by c square. Because I think most of the students are mathematics and mathematics background, and mathematics teachers are there. That m is equal to m naught by 1 minus v square by c square under root. Just you apply your mathematics skill by using binomial theorem. That's what m naught by 1 minus v square by c square root, you make it m naught into 1 minus v square by c square to the power of minus half. Remove the square root and expand it binomially, and take the first two terms of expansion and neglect the higher order terms by taking v square by c square as a beta square. So I can put it as like m is equal to m naught into 1 minus beta square to the power of minus half. And that 1 minus beta square to the power of minus half, if you expand, you will get 1 plus half beta square plus 3 by, I think some number 3 by 8 beta to the power of 4 plus dash I dash. Neglecting higher order terms and expanding, you will get that m minus m naught is equal to half m naught v square. You will get, just you try and verify. Then m minus m naught represents the change in mass. And here an indication is given by Einstein that mass of moving particle increases, and it is not constant. In classical theory, mass of particle always remains constant. But condition here, what condition? Because in formula, you are seeing that V and C. V is the mass of the velocity of the particle, like electron. It may be velocity of electron or proton or neutron and so on. And C is the speed of light. Speed of light, you know very well, that's the 3 into 10 to the power of 8 meters per second. And speed of speed of a particle, is it possible for us to make it to accelerate to move with the speed of light? Is not possible. No particle moves with the speed of light, no doubt in it. So under classical limits, then means we if you take for example like even if you take an aeroplane may go with the 540 kilometers per hour, or like you take to the extent of multiples of 18, that is 18 into 8, 144, 1440 kilometers per hour. But still, it comes out to be that 8 into, now you can calculate, it is going to be like 400 meters per second, and squaring 16 to 10 to the power of 4 by in denominator 9 into 10 to the power of 16. So the value is very negligibly small. That's why the higher order terms are ignored and only beta square term is taken. And by taking that formula m minus m naught into c square, you'll get it as half m naught v square. And somebody may ask, I think m minus m naught means if m is equal to m naught is the rest mass, means m minus m naught becomes 0 and half mv square is 0. The kinetic energy is 0. Kinetic energy is 0 means that, velocity is 0. So when particle is at rest, you cannot introduce the relativistic mass. So this is what the great thought given by Einstein. And now this mc square, though it is derived from theory of relativity, proved the same classically, because it has shown that it has half mv square. So he, now I think A is equal to h nu is equal to mc square. If mc square would not have been there, we would not have equated the h nu is equal to mc square. That's what the invention of Einstein came into picture. And now the de Broglie, as I said, de Broglie hypothesis. So what is the de Broglie hypothesis here? Light or electromagnetic radiation has a dual nature, because light was behaving as particle in some experiments. What experiments? I think we have mentioned photoelectric effect, one example, where that I think Einstein got the Nobel Prize, I said. Here, he took it as a particle. What is the name of the particle? Particle is photon. And a Compton effect, again based on, I think, the same, the particle behavior. Then X-ray photon, gamma ray photon, etc. This electromagnetic radiation was acting like a particle. And on the other hand, that's, the same electromagnetic radiation was behaving as a wave. This interference, diffraction, Bragg's law. The Bragg's law is what 2D scientific equal to n lambda. And then you have that, are we finding any term of a particle? The particle should be characterized by its position, mass, velocity, momentum, energy, and so on. And there is a sine theta, the trigonometric angle, and d is the interplanar spacing, and lambda is the wavelength. That's the wave term. So these all are successfully explained based on wave theory. So the electromagnetic radiation or light has a dual character, the particle character and wave character. So this is well established. Then this concept has taken by de Broglie, and de Broglie has stated that when photon is in motion, because photon always is in motion, because the light, we said, we cannot expect the light to stop, right? Because that means photon will be always in motion. And what is the speed of that photon? Always is the speed of light only. Say that 3 into 10 to the power of 8 meters per second. Then what is going to be different? The difference is that the wavelength, the energy associated with the photon, that E is equal to h nu, hc by lambda. Then h is a Planck's constant, and c is speed of light, and lambda is a wavelength. Then is equal to mc square. That's what I think Einstein's equation is equated, and we simplified the equation. That's what a photon of mass m moving the speed of light c possesses the energy mc square and is equal to h mu. And here what we have to think is, a moving photon is capable of producing its own wave, and is controlled by, again, its own wave. that the particle motion is responsible to produce a wave. However, the particle is controlled by wave itself. That is the beauty of de Broglie statement. And he equated both and simplified. And this is for light photon. That's why the lambda photon is equal to h by mc and h by p photon. And p photon means momentum of photon. That is a product of mass and speed of light. Then he applied the same for the matter. What is that matter? Basically, matter, as I said, that atomic and subatomic particles. So now the point is, okay, fine. I think here you can observe on LHS you have lambda term, that is a wave term. On RHS you have particle term. The photon means your MC, photon is a particle term. So that means there is a link between wave and particle. That's what how he has interpreted. And later the same is applied for the matter, and he replaced that momentum photon by matter particle. What is matter particle here? Suppose if I take electron, then wavelength of uh, matter wave, that is the matter wave produced by the electron motion. Then h by p means m into v, but this is not c. C is speed of light, and v is speed of electron. Now I think the speed of electron is in our hand. The speed of electron can be increased to any desired value with the application of the external energy in the form of applied potential. And that value you can increase from minimum to maximum depending on the requirement. And that's what h by mv and our momentum. And the basic formula, everybody is aware of that one. Momentum, like if we represent by p, small p, that p is equal to mv is equal, or that p can be interpreted in terms of energy, half mv square. Then I can make the E is equal to p square by 2m, or p is equal to under root 2em and 2e small m. Then capital A is the energy in terms of electron volts. Why we have taken electron volts? Because we are applying the voltage for electrons and it is becoming electron volts. So h by square root of 2 mev, that's for electron, and velocity, the speed of electron is 2 ev by m. This is what given by de Broglie. And now coming to the question is here, in case if a wave is produced by the electron in motion, there should be experimental evidence. And that experimental evidences uh, were explained by two scientists. One is Davison and Germer, the other one is G.P. Thomson. Okay, one is, I think, low speed electrons, and relatively, the second one is little high speed electrons. That's the G.P. Thomson experiment. In both the cases, they proved that electron is exhibiting wave when it is at a particular, I think, value, by satisfying the wave theory and the particle both, substituting the values of lambda. This is from de Broglie wavelength. They could get the exact values with the wave theory as well as the particle theory. This is what is mentioned here. Okay, fine. Now the point is, the electromagnetic radiation was based to take matter particles or matter waves. Then experimentally proved that the matter waves are produced from the matter particles. Now the point is that there should be a mathematical model and a mathematical equation. That mathematical equation, I think, was explained by the great, I think, scientist Erwin Schrödinger, who developed the mathematical differential equation. And by solving this one, you can get the equation as d square psi by dx square plus 8 pi square m by h square into minus v into psi is equal to 0, where psi represents the wave function, and it describes, psi is basically displacement, and it describes all the properties of wave, like amplitude, frequency, phase, then comes to energy and so on. And by looking at this equation, mathematics people easily can understand. I think various applications are there in electronics, like tunnel diode or like a few other devices can be explained successfully from the Schrodinger equation. And in fact, any quantum mechanical solution will be explained by Schrodinger equation. That is, of course, in one dimension is mentioned. Only x is there. Otherwise, it is d square psi by dx square plus d square psi by dy square plus d square psi by dz square plus this. I think this term remains same is equal to 0. Or del square psi plus whole thing is equal to 0 is the fundamental differential equation in quantum mechanics, and which is similar to that of the Newton's second law of motion, F is equal to ma. Without F is equal to ma, we can't even put a single step in mechanics to describe the motion of objects. And here also, to describe the motion of the quantum particle, quantum means here that photon particle, we need Schrodinger's differential equation. That's what. And later, okay, the size of wave function and wave potential difference is mentioned. And now for such a solution, psi, by looking at that equation, probably mathematics, the teachers easily can understand. The solution could be in the form of sine function, or it could be a cosine function, or combination of sine and cosine, and more appropriate, in fact, sine and cosine. And both can be replaced in terms of Euler's identity also, that Euler's formula in terms of exponential, that I theta. That's, very well, cos theta, I think, plus I sin theta. And by taking the boundary conditions, you can get the solutions, required solutions. And the macroscopic behavior, as I said, and classical Newtonian mechanics of position and momentum. We have the difference between classical and quantum. Here, that I think the importance of importance of Heisenberg uncertainty principle will come into picture. So, as long as the speed of object is finite, that is, when you compare with the speed of light, the speed of light is very high, I said. When speed of object or particle is small, you can find the position as well as velocity or momentum accurately. Simultaneously, both can be determined. That is according to classical theory. But when the speed of the particle increases and approaches to speed of light, then the uncertainty will come into picture. That is, it is not possible for us to identify the position as well as the velocity at the same time. Suppose if you focus on position, then velocity or momentum is uncertain, and whereas if velocity is certain and position is uncertain, that's how that Heisenberg interpreted. So the Heisenberg uncertainty principle came into picture in quantum mechanics. That's what here is mentioned. That classical in classical mechanics, these are, I think, that part is failed. When it comes to quantum mechanics, the de Broglie stated, like, de Broglie, according to de Broglie, a moving particle may be considered as a group of waves, and the particle may be located anywhere within the wave packet. The probability somewhere within the wave only, not beyond the wave, which indicates the uncertainty position of particle. And uncertainty is only for microscopic particles, you have to remember, not for macroscopic. And and of course, the statements are very simple statements. The product of uncertainties in terms of displacement and momentum is always equal to the Planck's constant, or I think greater than h by 2 pi. This is what. And the same principle is interpreted in terms of conjugate terms. The delta x, delta p. Delta x is the change in position, and delta p is the change in momentum. The same terms, I think it is analogous to delta E and delta T. That's what change in energy and the change in time. Delta E into delta T is equal to again h by 2 pi. Then other one is the in terms of angular momentum. The product of uncertainties in terms of angular momentum and angular displacement also equal to h by 2 pi. This is interpreted like these two. The other forms of uncertainty principles are. So, and these uncertainties anyhow that product is equal to h proved in fact experimentally also. By that time diffraction concept was established, and it took a single slit diffraction theory. That's what here single slit diffraction is given. This the d is the slit width, that is mentioned as a delta y, and electron the sharp electron beam is allowed to pass through the single slit and made to strike the screen. And this again, if you take the edges, from edges also you can show that the deviation from, and both the like that electron beams in terms of waves will be made to meet at n. That means at n both are going to be interfered, and from central magma to the point n is minimum. The condition of the single slit diffraction. Suppose if you take, how much extra path length that is traveled by the two, the second path is like the d sine theta is mentioned in figure. Then d sine theta is always equal to integral multiples of lambda, and from central maxima to the first minima is mentioned. Then n is equal to 1. You can get d sine theta is equal to, you will get lambda, and so that d sine theta lambda and sine theta is equal to lambda by d. The d is what? Delta y. That's what in the next slide it is given. That's what d sine theta is the path length difference between waves 1 and 2, and the waves interfere at point n on screen with minimum intensity. Minimum intensity means this section of waves takes place, and the sine theta is equal to lambda by delta y. But this sine theta, anyhow, that okay, fine. That's already explained. We place a slit of width d to the direction of motion of electron. The precision of the position of electron delta y in y direction is limited by the size of the slit. Delta y is equal to d, and the uncertainty in the electron momentum. There was vertical component that is taken in terms of momentum as delta py is equal to p sine theta, and the sine theta is taken as a lambda by delta y. In previous slide it is shown lambda by delta y, and I substituted here, and you could get delta y into delta p. Y is equal to h. That is the product of uncertainties in position momentum is always equal to the Planck's constant. That's why I started from basics the before 1900 and after 1900. That after 1900, I think totally the quantum dependent, that is matter dependent approaches. Previously, that all engineering branches, like mother engineering branch, mechanical followed by civil engineering, then electrical engineering, the chemical engineering, all were developed extensively, and I think from 1950, then I think 1930, 30, 40, 45 onwards, that semiconductors came into picture in terms of valves, then semiconductor devices, then semiconductor technology. Then in 1980, probably I think that computer concept came. Then when I was there in CBIT, I taught for first batch students of computer science, in fact, and this now I think the catching area is totally computers, of course, with the support of electronics, no doubt in it. And computers, especially, I think last 40 years, now rapidly changing. I think Madam Shobharani has explained. I was, I think, delighted to hear little the words, technical words, superposition, entanglement, then optimization. These all words. Then, like, okay, de Broglie, that concept also she, I think, took So everywhere you can come across these basic things that how we cannot forget our parents or the grandparents or like your forefathers and so on. Like quantum theory is the base. A strong foundation is laid by Max Planck, and the life for the quantum formula was explained by Einstein in different ways. Einstein, as I was mentioning, that m minus m naught is the concept of what difference in mass. Difference in mass means uh, that mass and energy can be convertible. If mass increases, the substance going to absorb the energy, and if mass decreases, it is going to be appeared in the form of release of energy. This is how interpreted the revolutionary concept, and this same concept is introduced in nuclear physics to work with the nuclear reactors. There's principle of atom bomb and so on. That is one kind. The other kind is a simulated emission was explained by Einstein in 1905, as I was telling, the revolutionary one, and it is the basic principle of laser. And in 1905, though it took 55 years to establish the lasers, types of lasers, and so on. That's what the great scientists, Einstein, Max Planck, along with Newton, can be remembered forever, for as long as this universe exists, as already I mentioned. And all, I think, the teaching fraternity and children, children means studies, the children who are studying and pursuing higher education, and who aim for research and the higher goals. And we all must take them as the inspiration, the great people, and we all must feel proud by ourselves to become part of these subjects. And here, I think, the only for the sake of inspiration is mentioned here. 27 scientists met in one international conference, that fifth Solvay, and out of 27 people here, 17 scientists were awarded the Nobel Prize. And here I highlighted Erwin Schrödinger, Heisenberg, then Niels Bohr, Lawrence Bragg, Louis D. Broglie, Max Planck, and so on, Curie, Einstein, and so on. And then coming to the history, now I request each one of you to look at this one. This, 75 years back, that great Einstein has given this uh, caption. I fear the day that technology will surpass our human interaction. The world will have a generation of idiots. And sorry to mention that one, idiots, because I think we are after technology, and if we don't run, I think technology will run over us, and we have to go in phase. But I think we have to protect our values and ethics before we we go fast. And even like the computer science area is now I think this year third year BTech people were forced to study cyber technology and artificial intelligence, and was insisted by university. So like that, I think okay, technology is fine. Then mechanical people or electrical people, whoever is joining in software industry, I think they are adopting technology. I think that, but we should not forget our basic principles, and we should not forget our ancient people. And thank you very much for giving me the opportunity, especially the mathematics section of CBIT. Thank you.
Thank you, sir. It was really inspiring to hear all the. You have taken us to the world of physics, sir. I want to quote one sentence here, sir, before I could say the vote of thanks. As we were listening to the things right from the beginning and we had some other things dominating our mind, you slowly pulled us into the world of physics and elevated us to the quantum world. We were enjoying the journey, sir, to be frank. You have made us revise the few concepts of physics we have learned long back in our graduation, like about Albert Einstein, and how he was confident of particle nature and de Broglie's hypothesis, how he connected the Planck's law of radiation and Einstein's mass energy relation. And you have even introduced us the concept of quantum photon particles, how the Schrodinger wave equation is more important with respect to the motion of the quantum photon particles. Really, sir, we have enriched our knowledge with all this. Hope to hear you again in future to gain some more knowledge. Sir, I have a small question. Can I ask?
Sure, madam. Sure. Thank you. Thank you very much. Please ask, madam.
Yeah. Other participants also, you can please go on for a question hour session. You can post your questions in the chat box or you can open your mic and speak up. Sir, as we know, this has been explored long back. Why the field have not gained momentum till recent century, sir?
Yeah, that's what, madam. Because the actual research took place after
Right.
1920 plus. I think that's what I told.
Yes.
Till 1927, nobody knows the existence of atom. The
Yes.
development took place after invention of this existence of atom, that was proved by Niels Bohr. Then coming to the basic principle and basic law is the quantum, the Max Planck's formula
Yes.
only. But of course, the Einstein is responsible in taking it as a particle nature. The particle nature was outdated for some time, in fact, because when wave theory became
Particular
yeah,
dominated.
yeah,
Yeah.
dominant. That's okay. That is one part too. That's why in 1927 you've seen, madam, one photograph.
Yes, sir.
Uh, that particular period only, the 30 years period, enormous research was done by the various scientists, and the fruits we are enjoying today, I think, whether in terms of VLSI or ULSI or Silicon Valley, and there are your computers and all these, I think are, have developed a lot from, I think, the 2000, after mobile revolution came in
Yes.
2000,
2000.
not before, I think, 2000.
Yes.
Now, present generations, really, it is a big challenge for them to go with the technology. And okay, but we had enjoyed, I can say, during our days. But I wish, I think, everyone is going to excel in upcoming domains and technologies.
Yes, sir.
So,
Yeah. Really, sir.
any
It
other question, please? Yeah.
yeah. Any participants, please? Please be interactive. You all can post your questions. Someone can speak up also. Okay.
Thank
Thank
you
you.
very
Thank you.
much, sir, for your excellent lecture in the FDP program. I am Suresh from CBIT, sir.
Yeah. I'm seeing. I'm seeing
Yes.
this. Really, very nice to see you all.
Sir, can you please suggest some tools for quantum computing practice purpose?
Quantum, as such, there are no tools, but basic tools are there. But I think in terms of the computer, like quantum computers and other things, I think yet to catch up the designing. I think still people are working, like using nanotechnology, applying to, like, large scale computers, and where you can apply the quantum concepts and all these things. Another, I think, I feel another 5 years it may take, 3 to 5 years.
Okay, sir. Thank you.
Is there anyone who want to post a question? Suresh, sir, shall we proceed?
Yes, madam.
Yeah. Now I think we'll have a break. Yeah. Thank you, sir. We are concluding with this session. I thank all the participants. We'll meet again for the session 3. It starts at 12:30 p.m. Thank you, one and all.
Thank you, ma'am.
Thank you.
Thank you, madam. Thank you.
Thank you, sir.
Okay, welcome, sir. Thank you.